I will start the recording then. So officially, not Happy Garbage Day, it's Thursday. I almost messed my own self up. So I had put up this a while ago. Do we all have a copy of this, either in paper or electronic form? Lecture 3, that's what we're looking at today. Sound good? Cool. All right. Then away we go. So to review, start with a brief reorientation as to where we are. So multi-level models for cluster data, that's the context where level 1 is people, level 2 is clusters. And that can take on a lot of forms, like that can be patients in hospitals, that can be students in schools, employees in businesses, take your pick. So there's a lot of instances in which people are grouped in naturally occurring units, and people from the same cluster are more likely to be related to each other than people from different clusters, and the model needs to understand that. So that's where we are. So we talked about an empty model as a starting point, where we have a level 1 model for the outcome for each person in each cluster. We then have a level 2 model for how each cluster gets their own mean as a starting point. So beta 0c here is a variable, but it's not an estimated parameter per se. It is a container for estimated parameters. So we have gamma 0, 0 as the fixed intercept, which becomes the mean of the cluster means. And then u0c, that is a value. So that is cluster C's deviation. So how far off are you from, is your cluster from the rest of the cluster means? That's what u0 is conveying conceptually. The estimated parameter for it is the variance across clusters tau squared. So that's what we're going to keep track of. How much was there to begin with? By how much did it go down? And then after we give each cluster their own mean, by adding in the fixed intercept plus the random intercept deviation, then that gets us to what the cluster's mean is, and we need to pick up the person. So then EPC is the remaining deviation of that person's outcome from the cluster mean that's predicted for them. And we assume that the variance across people and clusters is characterized by one value here. So homogeneity of variance essentially across clusters and people. That is a testable assumption. We're not going to get there this semester. That's what's probably by far the most common still. So then at this stage, have we explained anything? No, I would not say we have. What we have done is partition unexplained variance into 2 sources. What is at level 2? Reflecting between cluster mean differences that's captured by the random intercept variance. What is at level 1? Reflecting within cluster differences around those cluster means, which is captured by the residual variance at level 1. We can form intraclass correlation, so this is ICC1 in particular, as the ratio of between over total. So this is the proportion of total variance due to cluster mean differences. It's also the average correlation of persons from the same cluster. And there's one more that I would throw in here. It's an effect size for the amount of cluster dependency that you have due to mean differences. So you can think of it that way as well. And all we've done so far in terms of predictors is add fixed effects of level 2 predictors in this level 2 equation for beta 0. So those are main effects. They're cluster characteristics that would be constant across the people from the same cluster. And main effects or level 2 interactions among level 2 predictors can only predict random intercept variance because they are constant across the people. They can't explain people variance, which is down here in level 1. Okay, how are we doing so far? Is feeling okay? Anything you want to ask about? No. Okay. Then in terms of the example that went with this, I had a question earlier that I want to make sure I answer for everyone. So if I can just deviate very briefly from my plan here to go back to example 2. This is what you would be following to do homework 1. So I apologize the numbers don't match, but that's how it's working out this year. And I have a bunch of descriptive stuff here that I did in this example that I'm not asking you to do for homework. So everything that you need to do will be inside the starter syntax for your homework. In terms of the models, we went through empty models. So that's your first thing in your homework. And by the way, model 1 is your first multi-level model, not model 0. So if you go with the very first one, you will be confused. Easy mistake to make. And I think for the rest of the semester, though, there won't be like a model 0. Like, I won't start with a single level model. That was more for pedagogical purposes. So we did empty models. We did all the stuff that comes out of that. Do to do. And then we added level 2 predictors. So let me go to the model that has an interaction term in particular, because that was where the question was. So the very last one. So model 3 in this example adds an interaction between the size of the school as the cluster level predictor here, whether or not the school is public as the 0 or private as the 1, and then an interaction of the 2. So because these two predictors are both cluster things, their interaction goes in the level 2 model. Do we want to talk simple slopes? Would that be helpful to go back over, or are we feeling okay with that? This one's going to depend greatly on who you had intermediate with, quite frankly. I drill the crap out of this in my first year classes, but not everybody does. So, you want to go over it?
Yes, please.
You got it. You got it. So the rules for interaction terms. In interpreting what they do, you don't talk about what they do to your predicted outcome. You start by talking at what they do to your main effect slopes, and then they do stuff to the outcome. So there's like a layered process here. So in the equation, the effective size here, we would call this a simple main effect or a conditional main effect, because you can't just say this is the slope for the effective school size. That's incomplete. Given the interaction term right here, gamma O1 is only the slope for school size if the interaction term goes away. Otherwise, school size shows up here too. So that means, conceptually, this gamma O1 slope for school size has to represent the effective school size, specifically when private is 0, which means when you're talking about public schools. So this is the effective size in public schools. But what if you want to know what the effective size is in private schools? The interaction term implies that it should be different, at least to some extent. And to some extent is captured by the interaction term itself. So interactions are differences in slopes, always. And in homework that includes interaction terms, I always ask the questions in a specific order to emphasize this point. Like if this were your homework, you would get a question that says, what's the slope for public, what's the slope for private, and what's the difference? And the question is, I'm looking for you to recognize which of these are model parameters and which of these are linear combinations. So if I know what the slope is for public, gamma O3 tells me how different that slope is going to be for private. So if I want to talk about the slope of size for any kind of school, the rules for computing a simple slope are threefold. Step 1, find all of the spots in the model that have the predictor whose slope you want. So size here, and the interaction term, nope, hang on, this one and this one. This does not get included. The main effective private has nothing to do with the effective school size. The effective school size is what we're trying to go for here. So this is irrelevant. Likewise, the fixed intercept is irrelevant. It has nothing to do with school size. So those things stay out of the story. So grab all of the terms that have the predictor the slope is for that you want. That's step 1. Step 2 is to factor out that variable. So I factor size out of here, I factor size out of here, and then inside the brackets is what's left. So the effective school size starts off with whatever it is for public, and then we change it by the interaction term multiplied by the moderator, which is school type in this instance. So if private goes to 1, then the effective school size in private schools is gamma O1 plus gamma O3. And we can do that on a calculator just fine. The reason to go to the trouble to ask for it is so that you also get a standard error and a hypothesis test that goes with it. I could also go the other way. It's not as intuitive in this case, but I can also think of it this way. This is the main effect of public versus private, but I can't stop the sentence there. Given the interaction term, this is the main effect of public versus private, specifically for schools of the reference size. So the schools at It's actually 1,000, but then I scaled it into terms of hundreds. So when that goes to 0, then this is the slope of private. So if I wanted to know what the slope of private would be in a bigger school, I would say it's gamma O2 plus gamma O3 times whatever size I want to plug in here as the moderator. So all two-way interactions can be interpreted two different ways equally correctly. It's a substantive distinction as to what is the predictor and what is the moderator. It's up to you to describe it that way. So some of the things in here, the code in here is going to ask for this. Another thing that I'm doing in R that I don't have to do as Stata is recreating this hypothesis test. So the F that shows up here for the model is a joint test of all fixed slopes that are in the model. So that's why it's degrees of freedom 3 with Satterthwaite denominator degrees of freedom gives me a test statistic of 15. So this is the analog to the F test for the R square in regression. Overall, is the outcome that's predicted by these model fixed effects significantly related to the outcome for real? That's what this is answering. So in Stata code, I didn't have to ask for this joint hypothesis test. I call this a multivariate wall test using denominator degrees of freedom. F test is a more common term. F, in general, is a test that allows you to lump multiple slopes together. It shows up in a lot of different contexts. So it shows up in ANOVA if you have multiple binary contrasts that it takes to fully differentiate a bunch of group means. You might want to lump those binary contrasts back together for what's called an omnibus F test. In hierarchical regression, if you have a set of predictors and then you add another set of predictors and you want to test if the set significantly improves the prediction, that's an F test. They show up all over the place. So F is just a way to lump slopes together. The context changes what it's called. But the question then was, how do I recreate that F test in R? Or how does the code work that's doing it, I should say. So this is on page 9. So there's two things here that are using, these are what we would call post-estimation commands in Stata. Linear combinations is what I would call them in R, sort of more general. Any others? No? Okay. So contest 1D is the first one, contest MD is the second. These are both functions from the Elmer test package that was loaded at the outset of this example.
Is 1D for one dimension and MD multi-dimension?
I believe it is, yes. So the first one here, the 1D. Now what is happening is that you are giving multipliers to R to create linear combinations of your estimated fixed effects. So you have to know the order of your fixed effects as they appear in your output. Not as you wrote them necessarily, but as they appear in the output. So then this series of zeros and ones says the first one's 0, meaning don't do anything with the intercept. That's not relevant to me finding the effective school size for private schools, which is what I'm trying to do, the model implied simple slope for that. Because I want the effective school size, I do need a 1 in the second spot. So then what it's doing is, okay, start with 0.03. Don't do anything to the main effective private because what we're focusing on is the size slope and the main effective private is irrelevant, so we're going to leave that out, that's a 0. And then we put a 1 here for the interaction term because that's the value of the moderator that we want to multiply the interaction. So the 1 is because we want private to be 1 rather than 0 for public. So whenever you see multiple values in one of these little statements here, it's doing something to two different numbers in your output. If the numbers are positive, it's adding them together. So this is gamma O1 plus gamma O3. That is what's happening. It's a very roundabout sort of way, but that's what's happening, yes.
Is there a time where you would use, like, you want to include the intercept and then the one interaction term and then where they're being moderated and leave out the 1 and get a result and interpret that? I don't know, I'm just asking.
I can't think of an instance in which that would be useful, but you are limited only by your own creativity.
Well, that's why I was wondering, because you've got a lot of experience, I thought maybe you've seen something like that.
No, I mean, I've done a couple more sort of unusual things with this, so just let me play with this for a minute. Let's say that I had two different dummy codes for my main effects here, for instance. This would ask for the difference between them.
Mhm.
So subtraction that would be this one, the 1 minus that one. So then the reference for the comparison would be the minus 1.
So the difference between the second slope and the third slope.
That's what this would give me. So I had a homework assignment intermediate, for instance, in which, it was generalized, that's where it was. I had the number of manuscripts that you've published and the number of conference presentations you've made predicting the logit of getting a job. And so in that assignment, I asked for a comparison because I had number of papers and number of posters on comparable metrics. And so the slope comparison said, which is more impactful, adding one more paper or one more poster? And that's a question that's answered by testing the difference between their slopes. So whenever you have combinations of things, here, let me put this back. This is doing some kind of either addition or subtraction to the fixed effects in your model so that you can figure out simple slopes, model implied mean differences, and that kind of thing. So stuff that's in the model that's not direct. Now this one down here, contest MD, looks different. First of all, there's 3 of them. Separated by commas. The commas are doing a lot of heavy lifting in this code, okay? It's one of those things where it's like, no, you don't understand how important the commas are. So each of these has only one number in it. So we're not adding the slopes together. Like, we're not making a new slope out of old slopes. What we're saying is, hey, what if this were 0, and this one were 0, and this one were 0, all at the same time? It's a joint hypothesis test of all 3 slopes being 0. It's a multivariate test.
Why we need to know if all 3 slopes has a chance to be 0? Why we need that?
Because I would view this as the test of the significance of the model overall. So this answers the question, did my model successfully predict math scores? And I get an F test statistic of 15. There's the 3 slopes, denominator degrees of freedom, and a p-value that is 0 to many decimal places that says, yes, I do have a significant prediction. So why you would want to do 3 together, I think maybe is your question. Keep in mind what these slope estimates reflect: unique contributions. So this is the effect of each predictor after controlling for all the other predictors in the model at that level. At that level is the difference between this and regular regression. But if these 2 predictors were really highly correlated, it might be the case that it looks like neither one contributes on its own, but the redundant part that neither of them gets credit for could actually contribute to the model. I'm out of words, sorry. Hang on, let me get some words back.
Well, I'll throw out a phrase that will make a lot of people on your cringe.
Okay.
I just like, identity matrix with the 0 row on top.
I could show you the matrix
Yeah,
version
I
of
don't
this
wanna go there,
that
but-
actually does the multiplication, but I didn't think it would help.
No,
honestly.
I'm just saying, but I saw that just now.
Yeah.
Yep.
Yeah, that's what's happening under the scenes, is
Yeah,
that
yeah,
you're
yeah.
feeding information into a series of matrix operations.
Yes.
But yeah, keep in mind, so like R squares as measures of effect size reflect not just the unique contribution of the model predictors, but their joint contribution as well. So the F is trying to match that intent in terms of jointly and uniquely, how well did the model do as a whole?
So Lisa, ideally we want them to be significantly different because then they contribute in its own way.
I wouldn't say that. I think the example that I gave of contrasting the amount of the slope is different than the intent of putting them together in ways that make sense given the model parameterization. But does that help explain what the code is trying to do?
Yeah.
Okay, so how do you screw this up?
You don't put enough numbers.
You don't put enough numbers in.
You put the numbers in the wrong spots.
You put the numbers in the wrong spots. You copy and paste, and you forget to change the name of the model, so it's pulling the wrong number of spots.
Mhm.
There's a lot of ways to screw this up.
Yes.
And honestly, like,
I did all of those.
in your homework, you'll know because it'll turn green or red, right? But in life, you're not gonna know that. So in all honesty, like if you understand conceptually what that code should be doing, like I should get this number plus this number, like that's what I'm asking for. And if I get my calculator out or use R or Stata as a calculator and compute this, then I know what I should be getting back out of that contest 1D. I could compute the standard error manually. I would not recommend it. It's possible. It's not, the formula is not that ugly, but as you can see, the numbers get real tiny. So if you're doing things with printed output, you're going to lose precision real quick. So let the software do it, is the answer to that. Okay, I think that's, yeah, and then the rest of these are my functions for R-squares that are fairly straightforward. If you're interested in seeing how those work, you can look in the actual online files. It just stacks the two variance component tables and computes the differences. It's not elegant, it's effective. All right, any other questions on that? Okay, then I will let that one go. Back to lecture 3 for a minute. So let's start out with, speaking of ways to screw things up, what not to do. In bold giant font here. So level 2 predictors, I'm going to be abbreviating briefly with just L2X here for something generic with the C, versus level 1 predictors, L1X with the PC, because level 1 is per person, level 2 is per cluster. What if we just add in a level 1 predictor in the same way that we added in a level 2 predictor? So we have a level 2 predictor here. I have minus C with the 2 here as the constant that you would center this at. So that's just remembering the idea that for all predictors, we want 0 to be a meaningful value so that the fixed intercept has a reasonable interpretation. And I have a fixed slope here. What if I extended my level 1 model? So I have a beta 0 as the first term. Counting up, I can add a beta 1. This would be my level 1 predictor measured per person per cluster. And I may subtract some constant so that 0 means something, such as the grand mean or the minimum of the variable. Okay? So what this looks like it should do is like, well, gamma O1 is the fixed slope of level 2x. Gamma 1O is the fixed slope of level 1x. Not confusing at all, right?
No, not at all.
Think of it as a grid.
Mm-hmm.
So in the first level 2 equation for beta 0, because what we're predicting is beta 0, everything in this level 2 equation starts with a 0. So the first subscript controls where we are in level 1. The second subscript controls where we are in level 2. So gamma O1 is the first slope predicting beta 0. The next one would be gamma O2, O3, etc. The new term that we added, beta 1 here, we're adding only a fixed slope in this example to start with. And because we're predicting beta 1, that fixed slope starts with gamma 1. Because 1 is in the first spot for everything that will go into this level 2 equation. And this is essentially the starting point or the intercept of this level 2 equation, so that's why it's a 0 here. If I added another predictor, like right here where my mouse is, can you guess what numbers its subscripts would have?
Gamma 1 something.
1 something.
Well, and just depending on where you are in your list.
Yeah, I'm right here. So if it's in...
1, 1.
Yep, if it's in beta 1's equation, everything starts with a 1. The first predictor of beta 1 would be gamma 1, 1. That is actually going to form an interaction term if we follow that logic through, but not today. That will eventually be there. So if you just look at this and you look at the symmetry between what's happening for the level 2 slope and the level 1 slope, you'd be like, what's the problem? This seems reasonable. However, it is very likely to be misspecified for the same reasons that we needed a multi-level model in the first place.
Because if you wrote it all out, there's nothing distinguishing 1 from 2, really.
Exactly.
I mean, as written.
Exactly. So if you think about y here, we are saying that y is part people variance and cluster variance, right? We've got e's, we've got u's. What are we saying level 1x is?
It's specific for a person.
Yeah, it's only people things.
Uh-huh.
What are the odds that people characteristics are only people things and not also cluster things?
Very high.
Not very likely. Only in very specific, highly controlled contexts would you see something like that happen. Trying to think of examples. Let's say that you had whether a child was in 3rd grade or 4th grade in your school. Every school in your sample probably has 3rd grade and 4th grade in it. So which grade you're in doesn't necessarily have school level variance, unless you want to think about, does your school have more 4th graders than another school has? Like then that would be school variance, but it would be less likely in that case. Same thing if you go with binary gender. Like in the population, it's roughly 50-50. So unless you have a school that's an all-boys school or an all-girls school, you would expect 50-50-ish. So there may not be school level variance in gender because across schools, the balance is relatively equal. The effect of gender can vary across schools, but that's a different animal. In contrast, if you have something like the number of kids or whether or not you as a child get free lunch, so that's a person thing for sure, but schools vary quite a bit in the proportion of their kids that get free lunch. That's an indicator of lack of resources and all kinds of other things that go along with that. So if I put in free and reduced lunch here, for instance, and I'm saying that it's only a people thing, then I'm also saying it doesn't matter what kind of school you go to. It doesn't matter if your school is full of poor people or not. That idea of the school and the school's composition mattering above and beyond the person is what's going to be called a contextual effect. And if we don't put anything with respect to our person predictor in the level 2 model, we're saying there is no contextual effect, that just which person you are is all that matters and what school you go to doesn't matter at all. It's not likely to work that way. So that's the problem. We don't have an analog here for level 1X of E versus U. This is assumed to be all E, essentially. Question?
No, I was just going to say, that's why I was like, when I was working on the homework, I was like, I feel like there's nothing different than what we did before because we were treating it just like before.
Level 2 predictors are not different than before. It's just like
It's
straight
just,
up.
You just pushed them down.
Yeah, straight up single level regression in all the concepts. There's nothing different about it. It's level 1 that's the beast. Yep. So continuing on. So every clustered data textbook that I'm familiar with, including the one that I use in this class, which is now at the library, by the way, socioeconomic status, or SES, is a variable that's always in these things. And interestingly, in the data that we're going to play with, it's not only continuous, but it's centered at its mean is 0. So
that's a very weird location to be centered at.
That is a made-up variable, I'm 100% certain. But let's just go with it, okay? Sure. Take your favorite numeric index of socioeconomic status and pretend that's what we're talking about. So it is the case that some kids are better off than other kids, even amongst kids from the same school. So we would say that SES then has level 1 within cluster variation. So the question is there variance across children from the same school? Okay, that's the first thing here. And then, is there variance across schools in their average SES across their students? Are some schools poorer or richer than other schools? So each of these levels having variance is a logical prerequisite to that variance in the predictor relating to the corresponding variance in the outcome. So you got to have variance before that variance can become covariance with something else. So putting that into terms that we are familiar with, our friend intraclass correlation, ICC-1 in particular. If you are handed a data set and you have no idea at what level these variables are measured, you can either do things with like looking at the lengths. What was the thing, Vladimir? Was it length something, unique something?
Yeah.
Something like that?
But that's not good, I think.
It's an option.
Yeah, but if you have missing data, you will have a different number of unique values. So I think
that's true.
The ICC is the best option.
Okay, so yeah, missing data can ruin the plan of looking at links to determine such things.
Yeah.
But if you fit an empty model for each of your variables, treating it as if it were an outcome, And I actually recommend that people do this even in data sets they're familiar with, especially for things that they know are measured at level 1. ICC tells us how much of that variable is level 2 between. So if the ICC is less than 1, meaning there's at least some within, and if there is at least some within level 1 variation, then it can have a level 1 within cluster slope. Differences between people from the same cluster in the predictor can relate to differences between people from the same cluster in the outcome. If the ICC is greater than 0, then you know it has at least some level 2 between cluster variation, and therefore it can have a level 2 between cluster slope, meaning the average amount of the level 2 predictor for a school can predict the average level 2 outcome for a school. So having variance at that level is a logical prerequisite to then showing slopes at that level. So this would be the first thing I would check is, can it have a level 1 slope, can it have a level 2 slope, or can it be both? In the level 2 predictors that we were looking at in your homework and an example 2, what would their interclass correlations be? For a level 2 predictor, if I pretended it was an outcome and I fit an empty model for it, what would its interclass correlation be? Give me a finger question. 1 or 0. There's really only 2 choices here, right? Yeah, it's 1. Yeah, a level 2 predictor is all cluster differences, all between. It should have an ICC of 1. And so under this organizational scheme, we can't possibly have a within cluster effect of something that doesn't have within cluster variance in the first place. So as long as we have an interclass correlation somewhere between 0 and 1, we know we need to worry about this. So let's talk about slopes then. It could be the case that within level 1 effects and between level 2 effects operate in the same direction. So if we think about SES relating to achievement in students nested in schools, within cluster, kids that have more money than other kids in that school may have higher achievement. That may happen. Between schools, if you think about the average SES as a predictor in and of itself, schools that have more money on average, schools filled with rich kids, if they have more money on average than other schools, they may have greater mean achievement than other schools. And honestly, this is the level of inference that student end-of-grade test scores are designed to tap. They want to make decisions and evaluations about how well the schools are doing, what proportion of students are proficient or meeting expectations, or those kinds of things. Student-level data is used to make school-level inferences all the time. That's what they're trying to do. It may also be the case that slopes operate in different directions. And I stole this example from Kern and Bauer because I really liked it. The story that I heard about this example is that he was listening, Patrick was listening to NPR on his way to work, and they were talking about this situation, and he's like, oh my God, this is a between-within problem. So like any good statistician, they brought the example to their class. So within a species, relatively bigger animals have a shorter life expectancy. So overweight ducks are going to die sooner than healthy weight ducks. Larger species, however, tend to have longer life expectancies than smaller species. So whales live longer than cows, and cows live longer than ducks. So is being bigger, better?
That's interesting.
Right?
Yeah.
In my lifetime, so I have a little brother who's 6 feet tall, and I'm a short person, as you're well aware, although I've been told that I have tall person energy, because the people who only see me on Zoom always say, I thought you were taller. So yeah, I got tall person energy. I'm at 5'4". Well, my little brother outgrew me at 6 or 7 or something. Like, we were similarly sized. And so then the question is is she small or is he big? Like, how are you guys the same size, right? And so it's well, relatively speaking, right, he's big for his age and I'm small for my age, and it works out. But this kind of thing can get you to recognize real quick, hopefully, that hypotheses have to be specified at levels, right? So is it that resources are a person thing and resources lead to differences in whatever, or are resources like a proxy for some higher level, like societal thing that have different outcomes? Like at what level does SES matter? At what level does size matter? There's another one that I don't know if I thought of this or stole it from somewhere else. I'm honestly not sure at this point, but I'll just give you another example. I think I put it in my book though. Exercise and blood pressure. So if you are, you go to the doctor and they check your blood work, they check your vitals and things, blood pressure being low is a sign of health. Like high blood pressure is bad for you, right? So healthier people have lower blood pressure. But when you're actually exercising, your blood pressure is higher than when you're at rest. So is high blood pressure good or bad? Chronically high, bad. Instantaneously high, good, because then you're getting exercise. So in multi-level data, we have to think about what the relationships are among the variables at each level, because it may not represent the same thing conceptually. These variables have different meanings. Average blood pressure is a proxy for overall fitness. Current blood pressure is a proxy for like biological activity. But then also, these variables have different scales. So if you think about what a slope is, right? Let's do an old-fashioned review. What's a slope?
Change in y based off of change in x.
Yeah, change in y for a 1 unit change in x. And if we wanted to create a standardized slope, which we're not doing in this class, but you might have done that in intermediate or other classes, you need to know what the standard deviation of x and y are, right? To standardize your slope. Okay. Well, why am I not going to give you standardized slopes in this class? What's my standard deviation of y? Is it original y? Is it the standard deviation of the e part of y? Is it the standard deviation of the u part of y? Same thing with the x. So only in the situation in which these things are on the same scale, x and y, and they have the same relative breakdown of between versus within, is there even a chance that these slopes could be equal. Like numerically, these are on different scales because they're both relative to the variance at level 1 in the predictor and outcome and the variance at level 2 in the predictor and outcome. So these slopes are not going to be the same across levels. And they might be like coincidentally, but as a general principle, it's not going to work. All right, we did that. Okay, vocabulary time. How are we feeling so far, folks? Good? Good? Yeah. Okay. Okay is good. No, this is a lot. This is one of those things. It's just like, today is a day, I got to tell you. I got to do null hypothesis significance testing in the next class, which is like the hardest thing ever to teach. And then I got to do this in this class.
That is a challenge and a half.
This is a day, let me tell you, folks. I'm teaching intermediate, and we're doing null hypothesis significance testing, which honestly, like, you forget how many layers there are to following that logic. It's like an 8 layer thing to get to the p-value at the end. So, anywho, this is kind of similar. So you're going to hear me say all the synonyms stacked together to help you with the working memory load for this. So level 1 within, like level 2 between, because we got to hang on to all those pieces for this to make sense. So here's a new vocabulary word. What do we call this slope that reflects the idea that there's all just level 1 within E variance in this predictor? I call it smushed. And that term came about because I always make this gesture that you should have a level 2 slope and a level 1 slope, and instead, you got this. They're smushed together as one number. It's a classic omitted variable problem. X at level 1 is both a cluster thing and a people thing. Nevertheless, you are giving both halves of that variable essentially one slope instead of 2. That's the problem. So I call this a smushed effect because, again, it feels very descriptive. Conflated is the next best choice, in my opinion. I like that one. That's Chris Preacher's word. I'm not sure if he invented it or just popularized it. Not sure. Convergence is one that comes from the cognitive aging literature that I got acquainted with first as a postdoc. That refers to the idea of people measured at different ages or grades on purpose, what's known as an accelerated design. So I grab like a bunch of 3-year-olds, 4-year-olds, 5-year-olds, and I measure them for 5 years. You're hoping that their trajectory sort of converges onto like one common line. So a convergence effect would be like, what is the effect of age disregarding where you entered the trajectory at? And so you're hoping that that all converges together. Another one I've seen is composite. I don't like that one because that means about 7 different things based on your context. So smushed or conflated are the ones that I would have you used. And I gotta say, like, you know, in Mean Girls, like they say, tell Gretchen that fetch is never gonna happen. You know this reference? You should look it up on the YouTube if you don't. So there's a circa 1999, maybe? No, I was a postdoc when I saw that movie. So 2003 or 4, there's a movie called Mean Girls. And there's one character who's trying to make an expression fetch popular. I have no idea what fetch means. I think it's supposed to mean cool. And her friends are like, Gretchen, give it up. Fetch is never going to happen. Well, Gretchen, me, is making smushed happen. So there are like actual papers where there's like subheadings about smushed effects. And I was like, I did it. So proud of myself. You can put that on my tombstone. She invented smushed effects. Yeah. So this is what it is. It's a weighted slope. Because there are going to be so many more people at level 1 than there are clusters at level 2, it's almost always much more heavily weighted towards the within effect. So that means it's the between effect that's going to be screwed up. It's your level 2 model that suffers if you make this misspecification. And I have a side note here and a couple of articles on your reading list. If you've heard of what's known as the endogeneity program in other contexts, that is the idea that your level 1 predictor is accidentally correlated with your random intercept. And I say accidentally, meaning you don't want that to happen. And there are tests that you can use to check as to whether that happens. And in those fields, if those tests say whether or not something is that it's a problem, you're supposed to switch to fixed effects, meaning treat cluster as a categorical predictor in a single level model instead. Well, it turns out that that same set of concerns is exactly this. Because the only way that a level 1 predictor can be correlated with a level 2 anything is the hidden level 2 variance in the level 1 predictor. It's like a Trojan horse. Do you know that expression? Okay, that's another one to ask the Google about if not. It's like the level 2 variance is sneaking into the level 1 effect, and that's what's causing the problem. But it was not sneaking in, it's just already there. It's a failure to recognize that additional source of variance and to separately estimate its effect in the model. That's the problem. So it turns out if you don't smush, you're good. And you don't have to switch to fixed effects. So I usually get a question or two about this, which is why I have this as an aside. So I have, like I said, I have some papers on your reading list if you want to read more about it. But we can do proper model specification, avoiding smushed effects, still keeping random intercepts, and I'm going to show you how to do it. That's my plan. Where are we at here? 118. We're good to go. All right, graphically, this is what's happening. And I'm using color here quite deliberately. You're going to see lots of colors in this slide deck, okay? Green is for level 2 between. Purple is for level 1. So P is for purple. Can anyone think of a green word that starts with C?
I say cyan, but that's kind of a blue.
Yeah, cyan's like a teal, isn't it?
Yeah.
I don't know. I had PG for group, like when I first taught this class, but then the G's then it got grand, mean, group, mean, G, group, like it got bad. So I just kept the green and I switched it to C. Come up with
Cucumber, maybe?
Cucumber. Oh, I like that. That's good. I was gonna say like conifer, like is that like evergreens or something? Citron? I don't know. I like that one. Go with that. So green is level 2, purple is level 1. So like if you picture your stacked data set, right, you have your outcome Y, and it's some mixture of level 2 and level 1 because you have 2 different dimensions of sampling and you have variance left over after your fixed effects in each dimension. So the first thing we do is pull it apart. So I am using crossover event for those of you who in the SEM or who've been through the SEM. I'm using boxes and circles here quite deliberately. Boxes are observed things. Circles are latent or imaginary things, meaning model estimated quantities. Yeah.
And what are triangles? Sorry.
Oh, triangles are bullshit. That's what triangles are. I'm not putting the triangles in. No. Just no. You gotta draw the line somewhere. Triangles are to put the means in the model because it's a constant of ones. It's not a variable at all. So there's like a triangle and they put the lines in and anyway, no triangles in this class.
Sorry.
I know. I have thoughts. I have very strong feelings about the triangles. We have circles here because these are latent in the sense that the model is figuring out how much of the variance would be to due to U and how much is due to E. On the X side, though, we didn't do this first step. We haven't tried to split it out to figure out how much is green at level 2 or purple at level 1. And so when we put in an observed predictor and we put in a slope for it in predicting Y, what's actually happening behind the scenes is that we're putting in the same slope to predict the level 2 part of Y as we are the level 1 part of Y. In other words, the within level 1 slope is assumed to be the same as the between level 2 slope. So a 1 unit change in X has the same effect at both levels, even though what a unit is not the same at both levels. It's kind of crazy. So this is the problem. This is not a new problem. It's been recognized for decades. So here's another textbook. I adapted a formula that I found in there to describe how the smushed effect is computed. It is weighted by the standard error for the corresponding slope at each level, and that weighting process is why the fixed slope that you end up with is almost always a lot closer to the within slope. There's just more information there.
Mm-hmm.
So the 3 things that you might want to know out of a level 1 predictor then. In purple, at level 1, is there a within cluster slope? This is the thing that you put the predictor in the model to find out, right? This is the point of adding the predictor, is to answer this question. If you have a higher value of my level 1 X, so I'm a student, for instance, relative to my peers, if I'm higher than them in my school, is my outcome different than theirs too? So relative variation, if I'm higher than others in my school, is my outcome higher than others in my school? If so, then the level 1 part of that level 1 predictor is going to capture level 1 residual variance of the outcome. So within school differences on X relate to within school differences on Y at level 1. There's also level 2. So if I think about the average amount of my student level 1 predictor at my school, average SES, or proportion of students with this characteristic in my school. If I'm from a school that has more of X on average than other schools, do I have a higher outcome for my school than other schools? So does school mean proportion free and reduced lunch predict school mean achievement? This is a level 2 relationship, and as such, it should account for level 2 random intercept variance. So now in terms of pseudo R-squares, how many different are we talking about? If I have a level 1 effect, that's 1 pseudo R-square, right? I can ask, of the residual variance at level 1, how much did I explain by my level 1 predictor? And then at level 2, a second pseudo R-square. Of the level 2 variance in my outcome, how much did my level 2 predictors explain? There's a third one, and this is one that is sometimes harder to think about, but in cluster data is almost always of greater interest. There is another version of a level 2 slope, between and contextual. They're related, but they're not synonyms. Contextual you can understand a couple different ways. The easiest mathematically is simply asking, do the between and within slopes differ? The extent of their difference is the contextual effect, between minus within. So a contextual slope for their difference tells you if smushing is okay. So this is an instance in which we would have a -1, 1 in the model parameters, because we would have a 1 for the between, -1 for the within, and that would create a difference of the two slopes. And if a smushed slope is okay, meaning, if I go back to my picture, this line and this line are pretty much the same slope, like making them the same is not going to do any harm, then testing the difference between these slopes should result in a 0, or a non-significant difference. But let's say the between effect is a lot stronger than the within effect. If both of these are positive but of different magnitudes, then the contextual effect would be positive, meaning the between slope is more positive than the within slope. And just as there are 4 kinds of interactions, there are 4 kinds of contextual effects. Because relative to the within slope, the between slope can be more positive, more negative, or less negative. Same. There's a lot of overlap in terms of concepts here. So that's one way to think about it. The other is more intuitive if you think about people and context per se. So my son, 5th grade, at Wickham Elementary, I think we've discussed, right? Usman's kids go to Wickham.
There you go.
Yep. What grade are your kids in?
Pre-K and 2.
Pre-K and 2, okay. So what would happen if all 3 of us took our kids and we moved them to another elementary school? I don't know of any others in town. Can you name one? Anybody? No? Okay,
You'll go to Cedar Rapids.
Harn Elementary.
what is it?
Harn Elementary.
Harn?
Yeah.
Okay, Harn Elementary, great. Well, let's make some stuff up. A contextual effect would describe how much our kids' outcomes are expected to differ just from moving schools. Like if we took our kids and all their same characteristics and we dumped them in a new school, how would their predicted outcome change based on the contribution of that new school to their scores above and beyond their characteristics? Question.
Would that be like switching teachers for geometry class?
Yeah, that it would be a cross model more, I think, in that case, but yeah. Yeah, if you changed contexts, but you kept all your other same stuff, what is the extra incremental change to your score from being in a different context? That's what the context effects is. So like in one of the examples I'm going to show you, we will have free and reduced lunch at the student level. And so then a context effect would be, after controlling for whether you get free lunch, what is the extra contribution of going to a school where lots of kids need free lunch? Right? Is my math score predicted to be lower because I switched to this other elementary school where maybe the kids have fewer resources on average? Could be. That's the context effect. So the shorter way to do this is the between effect does not control for people characteristics when you estimate it, whereas the contextual effect does. I'll say that again. The level 2 between effect is the effect of the context without controlling for the effect of the individual. The context effect is the effect of the context after controlling for the individual. It's not like one is right and one is wrong. They mean different things. It can be very tricky to figure out which one you have. Very tricky, especially when you get into multivariate software. But usually people's research questions are more aligned with one way of thinking about it or another. So what is the extra contribution of going to a school that has these characteristics above and beyond mine? That's the context effect. So these are linear combinations of each other. You're going to hear me say this repeatedly. You're going to commit this to memory, I promise. Within plus contextual equals between. Between minus within equals contextual. Within plus contextual equals between. Between minus within equals contextual. That means I only need to know 2 out of the 3 to get the third. Linear combinations. So depending on how you set up your model, assuming you set it up correctly, there are multiple versions of correct, but let's just assume it's correct. You're either going to get within and between, or you're going to get within and contextual. And whichever level 2 version you don't have, you can get as a linear combination using those kinds of contest 1D type statements. So if you have a within contextual model, you would feed in a 1 and a 1 into that statement to add those 2 slopes together to make a between. If you got a within between model, then you would feed in a 1 for between and a -1 for within to make it go between minus within, and then the result would be your contextual effect. Vladimir?
Lisa, the contextual effect at level 2, is that controlling for the level 1 variable, the level 1 fixed effect, or both?
It's both. So the contextual effect is after controlling for the fixed effect of the level 1 variable in predicting the outcome directionally. And that is a distinction that won't matter in present tense, but for future reference, if you were to somehow estimate a model where you had the level 1 predictor in, but it was only correlated with the outcome, not directionally predicting it, then you would have a between effect at level 2. So it's not enough to have the variable in the story. It has to have a directional fixed effect to go with it. And that's, in fact, one of the techniques that I use in very complex models to figure out which one I have. If I change a slope to a covariance and it changes at level 2, then I know I had to have been contextual. Yeah. Okay. So, big picture. Why are level 1 predictors hard? Because they're not just level 1 predictors. That's the short answer. For the same reasons that we're doing multi-level modeling for an outcome that has 2 dimensions of sampling with variance left over at each kind, our predictor has 2 dimensions of sampling with variance of each kind. So we have to address the same kinds of concerns about differentiating what is cluster stuff from people stuff in the predictor as well as the outcome. How to do that is a different strategy, though.
That's why they were spending a month on this.
We're spending a month on this, give or take.
Yeah.
Unfortunately, in the longitudinal class, I never get to this. This is a topic for the advanced class because time and changeover time took like 3 months of the semester or something like that. So that's why this class is a different animal in terms of that, because we don't have that massive time design effect to worry about in this case. But here are 3 options to prevent smush slopes, to do it correctly. And I have them divided into what is possible in a univariate multi-level modeling framework versus multivariate. Now, what do I mean by that? In Stata Mixed, in our Elmer, you are predicting 1 column. Y, squiggle, model, right? That's what I mean by univariate, 1 column at a time. Now, your 1 column has information across people and clusters, but it's 1 variable. So if you are using software that is set up that way, which is every standard multi-level modeling package, then one of your options is what is known as cluster mean centering in this context, and what I call variable centering more generally, because this is a centering process in which you subtract a variable, not a constant. We are manually separating out the level 2 variance from the level 1 predictor. Like, brute force, carve it up. That's what we're doing. If you do this, you do the work ahead of time to ensure that your level 1 predictors are only level 1 predictors, and your level 2 predictors are only level 2 predictors. Therefore, the only possibilities that you can get back are within slopes and between slopes. Everything is level specific. I like this way best. It is the easiest to not screw up, especially when you're first starting out. The more common answer, it is way easier to screw up. What is commonly known as grand mean centering, but what I call constant centering more generally, because this is putting in the level 1 predictor and subtracting a constant, not a variable, just like you would like subtract 12 to make the reference to someone with a 12 or that kind of thing. So it's not different. People usually pick the grand mean as the constant, but they don't have to. And if you uncenter your variable, if you leave it alone, that's the same thing, because you can say that you centered at a constant of 0. So if you do nothing to your predictor, but you add in its level 2 cluster mean, that's the kicker here. You have to add in a separate variable. Then what you get back is a level 1 within slope and a level 2 contextual slope instead. So each of these is two alternative ways of setting up the model that are complementary in what they give you at level 2. So I'll show you each of those. The third we're not going to get to this semester because it requires multivariate software such as is used in M+. It requires the capability to predict more than one column at a time. If your software has that capability, then you can predict X as a variable and let it get carved up into circles in the same way that you predict Y as an outcome and let it get carved up into circles. That is what is known as latent centering, because you are centering at a latent variable rather than an observed variable.
Is this something that would not even be covered in Jonathan's current course?
You will not get to this, no.
I figured as much, but I just wanted to, this
Yep.
would be like advanced.
This was covered in the advanced longitudinal course. And at the very end, I tried to shove this into like the last week of this course 2 years ago. Erica's laughing. That went well, didn't it? It's the end of the semester. We're all exhausted. Let's do this real new hard topic as fast as we can. Question?
So you said for the centering, I know before we manage the constant to centering,
Mm-hmm.
but is there a trick what's the constant we pick? I think you mentioned a while ago that it depends on how we interpret it.
Mhm.
But then is there?
Yeah, so there is no wrong answer for what constant to pick. You pick it based on the interpretation that you want to make, because you're controlling what happens to the fixed intercept in particular. Once we add level 1 predictors with random slopes, then you're also conditioning the random intercept to be at 0. So if you pick a constant that's really far away from the data, you can screw things up. But generally something in the middle is fine, or if 0 already means something, like if your predictor is, the number of times you were late to class, some people are never late, they're a 0, right? That'd be fine. It's just an interpretational thing. By the way, you know this already as person mean centering, if that helps.
Yeah.
Same concept, different levels. Yep, yes. Okay, so, and we will re-go over this next week, to be fair. I'm not going to assume that this is going to land perfectly. We'll do it in layers. But here's cluster mean centering. You are literally carving up your level 1 predictor into 2 boxes to represent its level 2 part and its level 1 part. That's what we're doing. 2 boxes, observed variables. So first things first, I take my data set and I ask the software to compute the mean across rows for all the people from my cluster. And I save that cluster mean as a new column to my data set. So in R, that's the function add unit means that we talked about and is going to be used throughout the semester. In Stata, that's 1 line of code. It's likeegen something by cluster ID to make this happen, and it just merges it nicely back in. So that's step 1, is you build this variable yourself. So you're creating the mean for that cluster of all the people in that cluster's score on your level 1 predictor. That's what this part means right here. So the mean of level 1x across clusters. And in notation in articles, you'll sometimes see a dot for that, like it's averaged over the people, like dot C. That drives me nuts. So I don't have dots.
As opposed, but they put that there to indicate that that's for all the people. In that
Yeah,
cluster,
and then we
right?
get into like dot, when it's like over,
it
and I'm
gets over.
stop it.
Yeah.
No, it's
Dot,
unnecessary.
oh, we gotta look this now.
Yeah, dot. I don't know what I'm talking about at this point. Yeah, 3 is too many. But this is the mean of that level 1x for cluster C. Okay, this is a new variable in my data set. Now, I still want to subtract whatever constant I need so that this variable has a meaningful 0. So if it already has a meaningful 0, great. If it doesn't, rescale it. Doesn't matter what you pick.
This is, in effect, centering that.
This is constant centering as usual.
Yes.
At level 2, that's your only option. Nothing else would make sense.
Okay.
So let's say that I pick the mean of this variable in my sample as my C2 constant. So then if that's how I set it up, a positive value, this stands for cluster mean x. Okay, that's what CM stands for here. This is the result of this transformation. So if I have a positive value of cluster mean x, that means my cluster is higher than other clusters on average. If I had a negative value, my cluster is lower than other clusters on average because I've centered at what average is. So a 0 value would mean a cluster whose average with respect to the amount of level 1x for its students. So that's the level 2 part. This same exact variable is going to go into the model in the other way of setting it up too. So either way, we're going to use this one. At level 1 then, I am building a new column called within cluster X, PC. So that's what that means. And it starts off with the original, or the OG level 1 X column, so PC here, minus this thing that we just found. So minus the cluster mean of that level 1 predictor. So that's what I mean when I say we are centering at a variable, not a constant. We are removing all the school mean differences from this variable so that what's left is purely relative within school information. So after I subtract the cluster mean, a score of 0 means that I'm average on this predictor with respect to my cluster. A positive score means that I'm above my cluster. A negative score means I'm below my cluster. But that's all I can say. Relatively high, relatively low.
Mhm.
Because what it's relative to is up here in the level 2 model where it belongs. So you get level 2, how'd your cluster do on average? Okay, adjust your score. Then at level 1, relative to your cluster, how did you do? Okay, adjust your score. So this method of centering, where I'm using the variable here at level 2 and subtracting it at level 1, renders these two new predictors completely uncorrelated. So CMX is pure level 2, within cluster X is pure level 1.
If you had a third level, would the L1 XPC also then be an average from something and then go down to the, or how would that work? Or sorry, you have to work way up. So you'd be like the average of your constants? Or how would that work?
Yeah, so let's go up instead of down. I
Yeah,
think that'll
let's
be
go up.
easier.
Yeah,
So
yeah,
let's
yeah.
say that we have students in schools and districts.
Okay.
So then yes, at level 1, it would be students minus school mean.
Mhm.
At level 2, it would be school mean minus district mean. And at level 3, it would be district mean minus some constant.
Okay, so the constant's always at the highest level, so
Yeah.
to speak.
Under this strategy, yes.
Yeah, this, yes,
Mhm.
yes.
So then at level 3, it would be like between district differences in X. Level 2 would be within district between school differences in X. And then level 1 would be within school between student differences in X. Yes, I have to close my eyes to get those words
I
right.
understand.
It's very tricky. And this is why when I'm saying like, you can't just talk about X, like in your results section, you're gonna confuse people. We gotta talk about school mean X, or student X, or district X. Like we gotta put the adjectives in front of it because you're gonna have multiple layers or levels of the same predictor. Yep, gets tricky. All right, 143. Questions or things you wanna hear again quickly as we wrap up for the week? Thumb check?
I'll go 45.
45, yeah, that's what I'm shooting for. I'm shooting for something in here. Yep, okay, cool. All right, then,
Yay.
hey, have good weekends. Thanks for being here.
I'll see you in this class next week, Thursday.
Yep, that works. Let me know if you need anything. Work on your homework. It's due Wednesday, okay? Cool. All right, bye for now. Bye for the recording.